Just weeks ago, January 2026, physicists at CERN and MIT made an announcement that may fundamentally change how we understand the universe's earliest moments. This isn't a minor update or a technical footnote. It's breaking news from the very edge of modern physics. And it's being called one of the most profound discoveries in particle physics in the past decade. Today, we're diving into a breakthrough that takes us back to the very first instance after the Big Bang, to a time when the universe was less than a microsecond old, hotter than the core of any star, and filled with an exotic state of matter that hasn't naturally existed for nearly 14 billion years. This discovery comes from an extraordinary collaboration between researchers at the Massachusetts Institute of Technology and scientists working at CERN's Large Hadron Collider in Switzerland. Together, they've achieved something physicists have been chasing for more than 20 years. For the first time ever, they have directly observed the wake patterns created by quarks as they tear through the primordial soup that once filled the newborn universe. At first glance, this might sound impossibly distant. Events that unfolded billions of years ago, lasting for mere fractions of a second. So why should we care? Because that primordial soup, known as Quark-Gluon Plasma, is the raw material from which everything emerged. Galaxies, stars, planets, life. By understanding how this matter behaved in the universe's earliest moments, we uncover how a featureless fireball evolved into the rich, structured cosmos we inhabit today. Here's the key result, right up front. The researchers found that when a quark moves through quark-gluon plasma, it generates ripples and shockwaves, much like a boat carving a wake through water. That simple image hides a profound revelation. It shows that this primordial matter does not behave like a gas, where particles move independently. Instead, it behaves like a liquid, and not just any liquid, but the most perfect liquid ever observed in nature. To understand why this changes everything, we need to take a journey. We'll begin 13.8 billion years ago at the Big Bang itself. Then we'll travel to Switzerland, where scientists recreate the conditions of the early universe using the most powerful particle accelerator ever built. And finally, we'll unpack the ingenious experimental techniques that allowed physicists to see something no human has ever seen before. This is a story about the birth of the universe, and how, at long last, we're learning to read its earliest footprints. Part 1. The Early Universe and Theoretical Foundations. Let's begin our journey at the very beginning, or at least as close to the beginning as we can get with current physics. 13.8 billion years ago, our universe began in what we call the Big Bang. But this wasn't an explosion in the conventional sense. It was the beginning of space and time itself. In the first fraction of a second after the Big Bang, the universe was unimaginably hot and dense. We're talking about temperatures exceeding several trillion degrees Celsius. That's about 100,000 times hotter than the center of our sun. At these extreme temperatures, matter as we know it simply could not exist. Think about what happens when you heat water. At room temperature, it's a liquid. Heat it enough, and it becomes steam, a gas. Heat it even more, and the water molecules break apart into individual atoms. Heat it still more, and those atoms lose their electrons, becoming a plasma. But in the early universe, the temperatures were so extreme that even atomic nuclei couldn't hold together. Inside every atom today, you have a nucleus made of protons and neutrons. These protons and neutrons are themselves made of even smaller particles called quarks, held together by particles called gluons. Under normal conditions, quarks are never found alone. They're always bound together in groups of twos or threes. But in the first microsecond after the Big Bang, it was too hot even for this binding to occur. The quarks and gluons existed in a free state, zipping around at nearly the speed of light, constantly colliding and interacting with each other. This created what we call Quark-Gluon Plasma. It was the first form of matter to exist in our universe, and for a brief moment it filled all of space. This Quark-Gluon Plasma phase lasted for only about 10 microseconds, 10 millionths of a second. As the universe expanded, it cooled. When the temperature dropped below about 2 trillion degrees Celsius, something remarkable happened. The quarks and gluons suddenly began sticking together, forming the protons and neutrons that would eventually make up all the atoms in the universe. This transition from quark-gluon plasma to ordinary matter is called the QCD phase transition, named after quantum chromodynamics, the theory that describes the strong nuclear force. Now, to understand what the researchers discovered, we need to understand a bit about quantum chromodynamics, or QCD for short. Don't worry, I'm not going to drown you in mathematics. Instead, let me give you the conceptual picture. You're probably familiar with electric charge. Particles can be positively charged, like protons, or negatively charged, like electrons. Opposite charges attract, and like charges repel. This is electromagnetism, one of the 4 fundamental forces in nature. The strong nuclear force, which holds quarks together, works somewhat similarly, but with a crucial difference. Instead of one type of charge, the strong force involves 3 types of what we call color charge. Physicists whimsically named these red, green and blue, though they have nothing to do with actual colors. These are just labels for 3 different types of strong charge. Quarks carry one of these color charges. Gluons, the particles that carry the strong force, are unique because they carry both a color and an anticolor. This means gluons don't just interact with quarks, they also interact with other gluons. This self-interaction makes the strong force fundamentally different from electromagnetism and leads to some really bizarre properties. Here's where it gets interesting. In electromagnetism, the force between 2 charges gets weaker as they move farther apart. That makes intuitive sense. But with the strong force, something strange happens. When quarks are very close together, the force between them becomes weak. They behave almost as if they're free particles. This is called asymptotic freedom, and it's why quarks can move freely in the extremely hot, dense quark-gluon plasma. But as quarks try to move apart, the strong force gets stronger, not weaker. It's as if the quarks are connected by a rubber band that pulls harder the more you stretch it. This is why, under normal conditions, you can never isolate a single quark. The force keeping them together is simply too strong. This phenomenon is called confinement. The critical temperature for the transition between these two regimes is around 170 million electron volts, which corresponds to about 2 trillion Kelvin or 2 trillion degrees Celsius. Above this temperature, you get asymptotic freedom and quark-gluon plasma. Below it, you get confinement and ordinary matter made of protons, neutrons, and other composite particles. Now, here's the challenge that physicists face. The equations of quantum chromodynamics are incredibly difficult to solve. The self-interactions of gluons make the mathematics highly nonlinear. In fact, for most situations, we can't solve these equations exactly at all. We need to use powerful supercomputers and a technique called lattice QCD, where we approximate spacetime as a grid of points and calculate what happens at each point. These lattice QCD calculations have been crucial. They predicted that the QCD phase transition should occur, and they gave us estimates for the critical temperature. They also predicted something surprising about the properties of quark-gluon plasma, which brings us to the concept of a perfect fluid. When physicists first started thinking about quark-gluon plasma, many expected it would behave like a gas. After all, at such high temperatures, you might think particles would just fly around independently, rarely interacting. But theoretical calculations, particularly those using sophisticated techniques borrowed from string theory, predicted something very different. Let me introduce you to a fundamental quantity called the shear viscosity to entropy density ratio, or eta over S. This is a measure of how fluid-like a substance is. Honey has a very high viscosity. It flows slowly and sluggishly. Water has much lower viscosity. Superfluids have incredibly low viscosity, flowing with almost no resistance at all. In the early 2000s, theorists using a remarkable mathematical tool called the ADS-CFT correspondence made a startling prediction. They calculated that there should be a universal lower bound on this viscosity to entropy ratio of 1 over 4 pi in natural units. This bound comes from considering black hole physics in higher dimensional spaces and applying gauge gravity duality to map those results onto quantum field theories. I know that sounds incredibly abstract, but here's the key point. This universal bound suggests that quark-gluon plasma should have a viscosity incredibly close to the theoretical minimum. It should be what we call a nearly perfect fluid, meaning it flows with almost no internal friction. A perfect fluid has a remarkable property. When something moves through it, like a stone thrown into a pond, the fluid responds collectively. Waves spread out, ripples form. The entire medium reacts to the disturbance. This is very different from a gas, where particles scatter independently and don't produce these collective patterns. Theorists, including Krishna Rajagopal and his colleagues at MIT, developed what's called the hybrid model to describe what should happen when a high-energy quark moves through quark-gluon plasma. According to this model, the quark should create a wake, similar to the wake behind a boat or the sonic boom from a supersonic jet. Here's how it works. As the quark moves through the plasma, it deposits energy and momentum into the medium. Because the plasma is a nearly perfect fluid, this energy can't just disappear locally. Instead, it propagates as a disturbance, a wave moving at the speed of sound in the medium. If the quark is moving faster than this sound speed, which it typically is, the disturbances pile up and constructively interfere, creating a cone-shaped wake pattern called a Mach cone. The angle of this Mach cone depends on the ratio of the quark's velocity to the speed of sound in the plasma. The strength and shape of the wake depend on the transport properties of the plasma, particularly its viscosity. So, if we could observe these wakes, we could directly measure fundamental properties of the quark-gluon plasma and test whether it really does behave as a nearly perfect fluid. But here's the problem that stymied physicists for 2 decades. How do you actually observe these wakes? You can't create quark-gluon plasma in a bottle and study it at your leisure. The only way to make it is to smash heavy atomic nuclei together at nearly the speed of light. When lead nuclei collide at the Large Hadron Collider, they create a tiny fireball of quark-gluon plasma that lasts for less than 10 yoctoseconds. That's 10 times 10 to the minus 23 seconds. A yoctosecond is to a second, as a second is to about 300 million times the age of the universe. In that incredibly brief moment, quarks and gluons are liberated from confinement. High-energy quarks race through this plasma. Then, almost instantly, the fireball expands and cools. The quarks and gluons bind together into hadrons, and everything flies outward to be detected by the experimental apparatus. Previous experiments saw hints of collective behavior. They observed something called elliptic flow, where particles are preferentially emitted in certain directions, suggesting the plasma expanded hydrodynamically like a fluid. They observed jet quenching, where high-energy quarks lost energy while traversing the plasma. These were all consistent with the perfect fluid picture, but they weren't direct evidence of wake formation. The fundamental difficulty was this: when you produce a high-energy quark through a collision in the plasma, you almost always produce it together with another high-energy quark or gluon going in the opposite direction. Both particles create wakes. These wakes overlap and interfere with each other. It's like trying to study the wake pattern of one boat while another boat is creating its own wake right next to it. The patterns get mixed up, and you can't cleanly see what either wake looks like on its own. What was needed was a way to produce a single high-energy quark, with nothing else going in the opposite direction that could confuse the signal. This seemed impossible because of momentum conservation. If you kick a quark in one direction, something has to recoil in the other direction. The breakthrough came from realizing that the recoiling particle didn't have to be something that interacts with the quark-gluon plasma. And that brings us to the brilliant insight that made this discovery possible, and it involves a particle called the Z boson. Part 2. The experimental breakthrough. Before we dive into the experimental technique, let me paint you a picture of where this research takes place. The Large Hadron Collider, located at CERN near Geneva, Switzerland, is the most powerful particle accelerator ever built. It's a circular tunnel 27 kilometers in circumference, buried about 100 meters underground. Most of the time, the LHC accelerates protons, and that's how the Higgs boson was discovered in 2012. But for about 1 month each year, the LHC switches to accelerating heavy ions, specifically fully ionized lead nuclei. Each lead nucleus contains 208 protons and neutrons bound together. These nuclei are accelerated to incredible energies, 5.02 tera-electron volts per nucleon pair in the center of mass frame. They're traveling at 99.999991% of the speed of light. When two of these nuclei collide head-on, hundreds of protons and neutrons are interacting simultaneously. The collision creates an incredibly dense, hot region of space. In the most central collisions, where the nuclei hit nearly head-on, the energy density reaches about 15 giga-electron volts per cubic femtometer. To give you some sense of scale, a femtometer is 10 to the minus 15 meters, about the size of a proton. This energy density is sufficient to melt nuclear matter into quark-gluon plasma. The fireball that forms is tiny, only about 10 femtometers across, roughly the size of an atomic nucleus. But in that tiny volume, thousands of quarks and gluons are liberated and interacting. The temperature is about 4 trillion Kelvin, making it briefly the hottest matter in the entire solar system, hotter even than the cores of the most massive stars. The fireball expands at close to the speed of light. In about 20 zeptoseconds, that's 20 times 10 to the minus 21 seconds, it's already starting to cool. By about 10 yoctoseconds, the temperature has dropped below the critical temperature, and quarks and gluons start binding together. By the time a microsecond has passed, the event is over, and all that remains are the outgoing particles flying toward the detectors. The detectors themselves are marvels of engineering. The compact muon solenoid, or CMS detector, is where this particular research was conducted. Despite its name suggesting compactness, CMS weighs 14,000 metric tons and is 21 meters long. It's built like an onion, with layers of different detector technologies, each designed to measure different types of particles. At the very center is a silicon tracking detector with nearly 200 million individual detector elements, each measuring just millimeters across. Surrounding this is a powerful superconducting magnet, creating a magnetic field of 3.8 Tesla, strong enough to bend the paths of charged particles so we can measure their momentum. Outside the magnet are calorimeters that measure particle energies, and in the outermost layers are muon detectors. During a heavy ion run, the LHC creates these collisions thousands of times per second. Over a month-long run, billions of collisions are recorded. But only a tiny fraction of these produce the special events that the researchers needed for this study. Now we come to the crucial innovation that made this discovery possible, the use of Z bosons as reference particles. Let me explain why the Z boson is perfect for this purpose. The Z boson is one of the carriers of the weak nuclear force, one of the 4 fundamental forces in nature. It's a heavy particle with a mass of 91 giga-electron volts about 97 times heavier than a proton. The Z boson is electrically neutral, and crucially, it carries no color charge. This means it doesn't interact with the quark-gluon plasma via the strong force. In the collisions at the LHC, occasionally a quark and an antiquark in the plasma collide with enough energy to produce a Z boson. By conservation of momentum, if the Z boson is produced with high momentum going in one direction, there must be something recoiling in the opposite direction with equal momentum. In most cases, that recoiling particle is a single quark. Here's the beauty of this setup. The Z boson passes through the quark-gluon plasma like a ghost. It doesn't interact strongly with the medium. It doesn't deposit energy. It doesn't create a wake. The Z boson simply decays into a pair of leptons, typically muons or electrons, which we can detect with very high efficiency. Meanwhile, the recoiling quark on the opposite side does interact strongly with the plasma. It deposits energy. It should create a wake if the plasma behaves as a fluid. And because the Z boson tells us exactly when and where such an event occurred, and in which direction the recoiling quark is going, we can use the Z boson as a tag to select events where we have a single quark traversing the plasma with no confusing background from other particles. The Z boson's lifetime is extraordinarily short, about 3 × 10 to the minus 25 seconds. It decays essentially at the point where it was produced. The decay products are what we actually detect. About 10% of Z bosons decay into a muon and an antimuon. These muonic decays are particularly valuable because muons are easy to identify, and their momenta can be measured very accurately. The experimental signature is very clean. You look for events where you reconstruct 2 muons with opposite electric charges. These muons must have an invariant mass close to the Z boson mass of 91 giga-electron volts. They must be well isolated, meaning there isn't much other particle activity around them, which ensures they came from a Z boson decay rather than from some other process. Once you've identified a Z boson candidate, you know that there should be a recoiling quark going in the opposite direction. You can then look at all the other particles produced in that collision and ask whether their distribution shows any special pattern relative to the Z boson direction. If the quark created a wake in the plasma, you should see enhanced particle production at the angles corresponding to the edges of the Mach cone, and depleted particle production directly opposite the Z boson, where the quark itself passed through. The data for this study came from the 2015 heavy ion run at the Large Hadron Collider. During that run, the CMS detector recorded approximately 13 billion collision events. Let me emphasize that number. 13 billion collisions. That's nearly 2 collisions for every person on Earth. But Z boson production is rare. Very rare. From those 13 billion collisions, the researchers identified only about 2,000 events containing a Z boson candidate. That's 1 Z boson for every 6.5 million collisions. This rarity is precisely why it took so long and required such a massive data set to do this study. For each of those 2,000 Z boson events, the researchers measured everything they could about the collision. They tracked hundreds to thousands of charged particles emerging from the hadronization of the quark-gluon plasma. For each particle, they measured its momentum, its direction, and identified what type of particle it was as best they could. Then came the analysis. The researchers needed to quantify whether there was a pattern in how these particles were distributed in azimuthal angle relative to the Z boson direction. They used a technique based on Fourier analysis, decomposing the particle distribution into harmonic components. The second-order harmonic, called V2, measures whether there's a cos 2 phi modulation in the particle distribution, meaning whether particle production is enhanced at some angles and suppressed at others with a specific twofold symmetry. The third-order harmonic, V3, looks for a threefold pattern. These coefficients are computed using sophisticated multi-particle correlation techniques that are less sensitive to statistical fluctuations and non-flow effects than simpler methods. The analysis also had to account for numerous background effects. Not every pair of muons comes from a Z boson. Some come from other processes, and these need to be subtracted. The underlying event, meaning the soft particle production from the general collision, creates a background that needs to be carefully modeled and removed to see the wake signal clearly. The researchers used multiple independent techniques to estimate and subtract these backgrounds. They used mixed events, where the Z boson from one collision is paired with tracks from different collisions, to construct a reference distribution that captures detector effects and acceptance but doesn't have true correlations from wake formation. They use sideband methods, looking at muon pairs with invariant masses away from the Z boson mass, to estimate contributions from non-Z boson processes. All of these techniques had to be validated against control samples. The researchers looked at proton-proton collisions where no quark-gluon plasma is formed to verify that the wake signal is absent when it should be. They varied the selection criteria to ensure the results were stable. They performed careful studies of systematic uncertainties from detector resolution, efficiency corrections, and modeling assumptions. After all this work, the answer emerged. There was a clear, statistically significant signal. Particles were not distributed isotropically in the hemisphere opposite to the Z boson. They showed a characteristic pattern with a depletion directly opposite the Z boson and enhancement at angles slightly away from exact back-to-back. This is exactly what you would expect from a wake created by a quark moving through a nearly perfect fluid. Part 3. Results and physical meaning. Let me describe what the researchers actually observed. When they computed the second-order flow coefficient V2 as a function of particle transverse momentum, they found non-zero values with high statistical significance. For particles with momenta between 1 and 3 Geiger electron volts, they measured V2 values of approximately 0.05 to 0.08. Now, 0.05 might not sound like much, but in this context, it's huge. It means that particle production varies by about 10% between the directions where it's maximal and where it's minimal. Given the chaotic nature of heavy ion collisions and the small number of Z boson events, observing such a clear pattern is remarkable. The statistical significance of this signal exceeds 5 standard deviations. In particle physics, 5 sigma is the gold standard for claiming a discovery. It means the probability of seeing such a signal by random chance, if there were no real underlying effect, is less than 1 in 3.5 million. This is not a fluctuation. This is a real physical effect. Moreover, the pattern showed exactly the right momentum dependence. Lower momentum particles, which are more strongly coupled to the collective flow of the medium, showed larger V2 values. Higher momentum particles, which are less affected by the medium, showed smaller V2 values. This momentum dependence is a clear signature that the observed correlations arise from hydrodynamic collective flow rather than from simple kinematic effects or fragmentation. The spatial pattern of the correlations also match theoretical predictions. The enhancement in particle production didn't occur at random angles. It occurred at specific angles relative to the Z boson direction, angles consistent with Mach cone formation for a medium with the sound speed predicted by lattice QCD calculations. Think about what this means physically. When that quark races through the plasma at close to the speed of light, it's like a speedboat roaring across a still lake. The plasma can't respond instantaneously. The disturbance propagates at the speed of sound in the medium, which is about 60% of the speed of light. The quark outruns its own disturbance, creating a shock wave, a Mach cone. The edges of this Mach cone are where the disturbances created by the quark constructively interfere. These are the regions of maximum disturbance in the plasma. When the plasma hadronizes and turns back into ordinary particles, these regions of maximum disturbance show up as regions where more particles are produced. That's why we see enhanced particle production at specific angles. The observed wake patterns were compared against several theoretical models. The hybrid model, developed by Krishna Rajagopal and his collaborators, provided the most detailed predictions. This model combines perturbative quantum chromodynamics calculations for how the quark loses energy through radiation and collisions with hydrodynamic simulations of how the deposited energy and momentum evolve in the expanding plasma. The hybrid model contains parameters that characterize the Quark-Gluon Plasma properties. The most important of these is the shear viscosity to entropy density ratio, eta/S. For a nearly ideal fluid with eta/S close to the conjectured lower bound of 1/4 pi, and with a speed of sound near the value expected for a relativistic plasma, the model predicted V2 coefficients in the range of 0.04 to 0.09. This is in excellent quantitative agreement with what was observed. The data point falls right in the middle of the predicted range. This agreement is not just qualitative, it's quantitative. The theory and experiment match at the level of tens of percent, which is quite good considering the complexity of the system. Alternative theoretical models that treat the quark-gluon plasma as a weakly coupled gas of quasi-particles predicted much smaller flow coefficients, typically below 0.02. These models don't produce strong collective effects because the mean free path in a weakly coupled system is long compared to the system size. Particles scatter independently rather than flowing collectively. The data clearly favor the strongly coupled, nearly perfect fluid description over the weakly coupled gas description. This is a powerful confirmation of the theoretical picture that has been developed over the past 2 decades based on lattice QCD, gauge gravity duality, and phenomenological studies of heavy ion collisions. The researchers also performed numerous consistency checks. They verified that the signal is absent in proton-proton collisions where no quark-gluon plasma forms. They checked that the signal strength depends sensibly on collision centrality, being stronger in more central collisions that produce larger, hotter plasma droplets. They varied the Z-boson selection criteria and background subtraction methods and confirmed that the results remain stable. All of these cross-checks support the interpretation that what's being observed is genuinely the hydrodynamic response of quark-gluon plasma to energetic quarks traversing it. This is direct evidence of wake formation, the smoking gun that physicists have been seeking for 20 years. Beyond simply confirming that wakes exist, this measurement allows researchers to extract quantitative values for the transport properties of quark-gluon plasma. By fitting the measured flow coefficients to theoretical predictions with varying input parameters, they can constrain quantities like the shear viscosity to entropy-density ratio. The analysis indicates that ETA over S for the quark-gluon plasma is in the range of 0.1 to 0.2 times 1/4 pi. This is incredibly close to the conjectured universal lower bound. It confirms that quark-gluon plasma is the most perfect fluid ever observed experimentally. For comparison, consider other fluids we know. Water has an ETA over S value that's thousands of times larger. Even superfluid helium, which was previously thought to be the most perfect fluid, has an ETA over S about 10 times larger than what's measured for quark-gluon plasma. The primordial soup of the early universe was more perfect than any fluid we encounter in everyday life or in condensed matter laboratories. This extraordinarily low viscosity has important implications. It means that quark-gluon plasma flows with almost no internal friction. When disturbed, it responds collectively and coherently. It reaches local thermal equilibrium on timescales of less than 1 femtometer over C, which is about the time it takes light to cross a proton. This rapid thermalization was crucial in the early universe. It meant that even though the quark-gluon plasma phase lasted for only microseconds, the system had time to thermalize and evolve hydrodynamically. This hydrodynamic evolution affected how matter was distributed and how density fluctuations propagated, ultimately influencing the formation of structure in the later universe. The speed of sound in the quark-gluon plasma can also be extracted from the angular positions where particle production is maximally enhanced. The Mach cone opening angle depends on the ratio of the particle velocity to the sound speed. From the measured angles, the researchers determined that the sound speed is approximately 0.35 times the speed of light. This value is consistent with lattice QCD calculations of the equation of state for strongly interacting matter at temperatures around 300 MeV, which corresponds to about 3.5 trillion Kelvin. It's also consistent with what would be expected for a relativistic fluid, where the pressure and energy density are related by simple scaling laws. These measurements of viscosity and sound speed represent some of the most precise determinations of quark-gluon plasma properties achieved to date. They constrain theoretical models and provide benchmarks against which future calculations can be tested. They also provide input for modeling other systems where dense quark matter might exist, such as the cores of neutron stars. Part 4. Broader implications and future directions. Let's step back and think about what these findings mean for our understanding of the early universe. During the quark epoch, from about 10 picoseconds to 10 microseconds after the Big Bang, all matter in the universe existed as quark-gluon plasma. The properties of this plasma that we're measuring in terrestrial experiments directly tell us about conditions in the early universe. The fact that the plasma was a nearly perfect fluid with rapid thermalization means that the early universe quickly reached thermal equilibrium at each point in space. This is a key assumption underlying the standard hot Big Bang cosmology. If the plasma had been weakly coupled with long, mean, free paths, local thermal equilibrium might not have been established, and the standard thermal history calculations would need to be revised. The low viscosity also has implications for how primordial density fluctuations evolved. These fluctuations, which we observe today in the cosmic microwave background radiation and in the large-scale distribution of galaxies, originated from quantum fluctuations during the inflationary epoch. As the universe expanded and these fluctuations re-entered the horizon, they propagated as sound waves in the primordial plasma. In a highly viscous medium, these sound waves would have been damped, potentially erasing density fluctuations on certain scales. The near-perfect fluidity of quark-gluon plasma meant that damping was minimal, allowing acoustic oscillations to persist. This is consistent with the observed properties of the cosmic microwave background, which shows clear acoustic peaks indicating multiple oscillations of the sound waves before the universe became transparent. The QCD phase transition itself, when quarks and gluons bound together to form hadrons, released energy and affected the expansion rate of the universe. Understanding the details of this phase transition requires knowing the transport properties and equation of state of quark-gluon plasma. The measurements from heavy ion experiments provide crucial input for refining models of this transition and its cosmological consequences. One of the most beautiful aspects of this research is how it connects different areas of physics that might seem completely unrelated. The fact that theoretical predictions for quark-gluon plasma viscosity come from calculations involving black holes in higher dimensional spaces is remarkable. This connection arises through gauge gravity duality, a profound relationship between quantum field theories and theories of gravity in curved spacetime. That we can test predictions from string theory and black hole thermodynamics using a particle accelerator on Earth speaks to a deep unity in physics. Certain universal properties appear to characterize all strongly coupled quantum systems near thermal equilibrium, regardless of whether we're talking about quarks and gluons, black holes, or even certain exotic materials in condensed matter physics. The study of Quark-Gluon Plasma also connects to astrophysics, particularly to understanding neutron stars. Neutron star cores contain the densest stable matter in the universe, with densities several times that of atomic nuclei. At these densities, QCD effects become crucial, and it's possible that quark matter exists in the very centers of the most massive neutron stars. Recent observations of neutron star mergers using gravitational wave detectors have begun to constrain the equation of state of dense nuclear matter. These astrophysical constraints can be combined with laboratory measurements from heavy ion collisions and theoretical calculations from lattice QCD to build a comprehensive picture of matter under extreme conditions across the full QCD phase diagram. This discovery opens many avenues for future research. The most immediate extension is to analyze larger datasets. The LHC has conducted additional heavy ion runs since 2015, and more are planned. With more Z boson events, researchers can perform more differential measurements, studying how wake patterns depend on various kinematic variables and collision properties. Another direction is to extend the technique to photon-tagged events. Photons, like Z bosons, don't carry color charge and pass through Quark-Gluon Plasma without strong interactions. However, photons are produced much more frequently than Z bosons, potentially providing much larger statistical samples. The challenge is separating true prompt photons from background photons produced by other processes. Future facilities will provide new opportunities. The proposed electron-ion collider would collide electrons with heavy nuclei, providing a cleaner environment for studying quark-nucleus interactions. The upgraded high-luminosity LHC, beginning operation around 2029, will deliver much higher collision rates and feature detector upgrades that improve tracking precision and extend coverage to larger pseudo-rapidities. There are also intriguing questions about small system collectivity. Recent experiments have observed hints of collective behavior even in proton-proton and proton-nucleus collisions, which create much smaller systems than nucleus-nucleus collisions. Whether these small systems form tiny droplets of quark-gluon plasma or whether the collective signatures arise from other mechanisms remains debated. Wake studies in small systems could help resolve this question. On the theoretical side, many questions remain. Understanding the microscopic mechanism for rapid thermalization is an active research area. Incorporating quantum corrections into hydrodynamic descriptions and understanding the limits of validity of fluid dynamics for small or short-lived systems requires developing new theoretical tools. Exploring the QCD phase diagram at high baryon density, relevant for neutron star physics, poses significant challenges due to computational difficulties with lattice QCD. Conclusion. Let me bring us to a close by summarizing what makes this discovery so significant and what it tells us about our universe. For the first time, physicists have directly observed the wake created by a quark moving through Quark-Gluon Plasma. This confirms a prediction that has stood for 2 decades but had never been unambiguously demonstrated. The observation was made possible by a clever experimental technique using Z bosons as reference particles, allowing researchers to isolate the medium response to a single energetic quark. The measured wake patterns match quantitatively with theoretical predictions for a nearly perfect fluid with extremely low viscosity. The extracted shear viscosity to entropy density ratio is within 20% of the conjectured universal lower bound, confirming that Quark-Gluon Plasma is the most perfect fluid ever observed in nature. These findings tell us that the primordial soup filling the universe in its first microseconds behaved as a strongly coupled, rapidly thermalizing, nearly inviscid fluid. This validates core assumptions of the standard cosmological model and provides quantitative constraints on how the early universe evolved. The properties measured in terrestrial experiments directly inform our understanding of cosmic history. The success of this measurement demonstrates the power of experimental particle physics to probe the most extreme conditions imaginable, recreating in the laboratory the state of matter that last existed naturally nearly 14 billion years ago. It shows how clever experimental design can overcome seemingly insurmountable challenges, in this case isolating a subtle signal from an overwhelmingly complex background. Looking forward, this technique opens new avenues for studying quark-gluon plasma properties with unprecedented precision. Future measurements with larger data sets and improved detectors will refine our knowledge of QCD transport coefficients and medium response. These studies will continue to connect terrestrial particle physics with early universe cosmology, neutron star astrophysics, and fundamental quantum field theory. In the grand sweep of physics, this discovery represents another piece of the cosmic puzzle. We've learned something profound about how matter behaves under conditions of extreme temperature and density. We've confirmed that our theoretical understanding of the strong nuclear force, as encoded in quantum chromodynamics, correctly describes nature even in regimes far removed from everyday experience. Most fundamentally, we've gained deeper insight into our cosmic origins. The quark-gluon plasma studied in these experiments is the same substance that once filled all of space. Understanding its properties helps us understand where we came from, how the matter composing our bodies and our world emerged from the primordial fireball of the Big Bang. This is why we do fundamental research, not always for immediate practical applications, but for the deeper understanding of nature it brings, for the connections it reveals between seemingly disparate phenomena, and for the profound insights it offers into the fundamental workings of our universe.